It's a pleasure for me to introduce to Misha Kapovich. He's going to speak about topology of complex projective varieties and three hyperbolic geometries.
Three-dimensional hyperbolic geometry. Okay, thank you for the invitation. It's always a pleasure to be here in Cuernavaca. So what I will talk about is this interaction between algebraic geometry, complex algebraic geometry on one side, and real hyperbolic geometries on the other side. And of course, there is one example that everybody knows. It's interaction between theory of complex curves, or Riemann surfaces, and hyperbolic geometry, real hyperbolic geometry in dimension 2. So here we are going one dimension higher. It's three-dimensional hyperbolic geometry and topology. And I hope I will state a theorem that will be new even to people who are doing three-dimensional topology, and there are a few of them here. So, but applications are in algebraic geometry. So let me, and again, I'm not assuming any knowledge of any of this, so I will try to give all the definitions, okay? So let's start. Motivation and sort of explain what all the terms are. A projective variety is a solution set, I will also always denote by Z, of a system of homogeneous polynomial equations in n+1 variables, which we project to the complex projective space. Okay. So, and for me, variety, I'm allowing reducible varieties. So it's, that's the definition I'm working with. And the issue of irreducibility will be one of the major themes of this talk. Okay, so the question is, what can one say about topology of such varieties? And for topology, I will only talk about fundamental groups because I cannot say anything else. Okay. So complexity of the fundamental groups. What can one say? So this Z is compact. Well, that's pretty much clear. And moreover, it admits a finite triangulation. So it's a simplicial complex. Finite simplicial complex. Therefore, its fundamental group is finitely represented. I mean, it's exercise that we all do when we learn basic algebraic topology. So FP will stand for finitely represented group. That's one obvious restriction on fundamental groups of projective varieties. Okay, so let's assume it's connected, so I don't have to put a base point everywhere. I'll just talk about connected varieties. So if this variety were smooth, so being actually differentiable being a manifold, then there are many restrictions on topology. The oldest restriction is from Hodge theory that all odd Betti numbers are even. Okay, it's kind of, so for example, first Betti number is even. So in particular, rank of abelianization of fundamental group is an even number. So for example, infinite cyclic group cannot be realized as a fundamental group of a smooth, complex projective variety. And there are many other restrictions. So for example, such a group cannot split as a free product, etc., etc. There is a small industry of studying restrictions on fundamental groups of smooth, complex projective varieties. So the question is, what happens if this Z is allowed to be singular? Okay. What are restrictions on fundamental group? So here is the, okay, so so on this diagram I put kind of various events which were happening. So this started with, again, it was probably known to Lefschetz. If my guess would be if somebody asked Lefschetz this question, he would provide an answer. But the first reference I found, the first place where it was really proven, it was Deligne's ICM address in '74. And I will explain Deligne's argument. It's beautiful and simple. So that's why Lefschetz could have known that. So that there are no restrictions on fundamental groups of, if you just say variety. If you don't assume irreducible, don't control singularities, no restrictions, apart from being finitely represented. So Simpson, and for a long time it was a question, can one get something better? Can at least one get irreducible variety? Because, I mean, if you ask an algebraic geometer, 99% of algebraic geometers will tell you that variety should be irreducible, otherwise it's not a variety. Well, I'm not an algebraic geometry, so I'm allowed to say variety even if it's reducible. Okay. So Simpson proved the following, that every finitely represented group is isomorphic to fundamental group of some irreducible projective variety. Okay, and that happened in 2011. It was an open problem for a while, until he managed to get irreducible varieties. And he asked whether there are restrictions on fundamental groups if, in addition to being irreducible, we require normal crossings. And I will explain what that means. I mean, these are the mildest possible singularities in algebraic geometry. It's kind of next to being smooth manifold. So in particular, he asked, is it true that every finitely represented group can be realized this way? Okay. So irreducible and normal crossing singularities. So just for those of you who don't, I mean, there are non-algebraic geometries, so that's why I'm giving. So normal crossing just means that locally the variety has the form, you have a product of variables equal to 0. So what does it mean? It's just a union of coordinate hyperplanes. That's the local picture of variety with normal crossings. For example, two hyperplanes meeting in three-dimensional space. That would be normal crossing. But for example, three lines meeting in one point, union of three coordinate axes in three-dimensional space is not a normal crossing. In dimension 2 it would be, but in dimension 3 it's not. Okay? Because these are supposed to be hyperplanes. Irreducible, again, just for the record, if you can represent, if you can break this into union of two subvarieties, then one of them is contained in another. Okay.
So normal crossing implies hypersurface?
No, you see, it's a local property. So, I mean, the Z sits in some, Z is not a hypersurface itself, but it's locally is a hypersurface.
For example, two lines in a three space.
Two lines in a three space is a normal crossing. Two lines in a three space is a normal crossing because it's biholomorphic to two lines in a two space. And that's, right, normal crossing. Again, so when I say has the form means it's biholomorphic too. So it has this local model. Okay, so for a topology, for an algebraic geometry, I don't have to explain why is it a good class, but for a topologist, so what's a manifold? Manifold is a space which has some kind of a canonical local structure, right? Being just Euclidean space. Normal crossing will give you a different kind of local structure, just union of hyperplanes. Okay. Well, why irreducible? For a topologist, most topologists prefer to study connected manifolds. I mean, so it's like being connected. So why is it like a manifold then? Well, you have a fundamental class then, right? If you just, so this thing will have a, just a top-dimensional homology will be cyclic. So it starts to look like a manifold, assuming it's irreducible. If it has several components, it will not have sort of correct homology in top dimension. Okay. So, but let's just say algebraic geometries like those. So here is the theorem. So that happened in 2014, that every finitely presented group can be realized as fundamental group of some reducible two-dimensional variety Z with normal crossing singularities. So notice that here it was irreducible, but singularities were bad. Here it's reducible, but singularities are good. Okay, so it was kind of going in opposite, in a transversal direction to what Simpson was doing. Actually, when we did this, we did not know about Simpson's work. I mean, I did kind of dig this, just found it by looking at what's known. Okay, right. So here is a corollary, which explains why, I mean, this whole collaboration, again, I'm not an algebraic geometer, as you probably realize by now. I'm a topologist, I'm a geometer, but I call myself geometric geometer. So I'm definitely not an algebraic geometer. I mean, Janar just wrote to me out of blue in summer of 2011, asking me, Misha, do you know if every group can be realized as a fundamental group of variety with normal crossings? My reaction was probably every group. He was hoping for opposite answer. He was hoping for abstractions. But in the end, so this is theorem which was, this is what Kohler was after. And the corollary of this theorem is that every finitely presented group, G, appears as fundamental group of a link of a three-dimensional isolated singularity. So the picture is, I will put it on the slide, but the picture is the following. So you have some three-dimensional complex variety Y. So again, where it sits, it sits in some high-dimensional space. And this is isolated singularity. If you remove it locally, it's smooth. Okay, and then we look at the link of this thing. Link, I mean, as a topologist, we just triangulate this and take a topological link of this vertex. As a geometry, we just take a sphere in ambient space, hypersphere, and look at the intersection. So the intersection is a manifold, a real manifold of dimension 5, because dimension drops by 1. So that's the link of the singularity. So this theorem says that absolutely any group you can imagine, I mean, within the realm of reasonable, because this is a compact manifold, so fundamental group better be finitely presented. So any group appears as a fundamental group of such a link. Again, Kohler was hoping for abstractions, and he kind of knew how to derive, how to relate. So again, my contribution was absolutely zero to this discovery. That was all Kohler's work.
Is this by a hypersurface?
No, it's not. Again, I should probably put here, so it sits in some Cn. And the sphere is 2n minus 1. Right, no, it's not a hypersurface. But it is an isolated singularity. So there is a little history behind this. Right, so again, it was all Kohler's work, but remark what happens if you drop dimension by 1. If you look at the two-dimensional singularities. So then in this case, again, suppose this is isolated singularity, then the link is three-dimensional manifold. And again, fundamental groups of three-dimensional manifolds are very, very limited. There's a very limited class of groups among finitely presented groups. But even among three-dimensional manifolds, these are very, very special three-dimensional manifolds. These are what's called weak graph manifolds. And this goes back to David Mumford. I mean, the notion of weak graph manifolds did not exist, but he proved something that Walthausen later on called graph manifold, and now it's called a weak graph manifold. So, and meaning for topology, this means that all geometric components of this link are Seifert. So there are no hyperbolic components. That's what it means to be weak graph manifold. It might not, again, I'm just talking about topologies in this group. So, I mean, this manifold has a connected sum decomposition and then toral decomposition into Seifert pieces. Right, so, but the bottom line is that in two-dimensional case, the fundamental groups are very, very restricted. So, but once you go one dimension higher, you can get any group you like. So incidentally, I will not have time to talk about this. This was Mumford's remarkable contribution to three-dimensional topology. And if you care, ask me after the talk. And the key word is, so there's a connection between Mumford and Perelman. So that's the key. How? Ask me after the talk. Otherwise, my talk will degenerate into something completely unintended. Okay? Don't ask me now, please. Okay, this is the picture which I already drew. This is the link of isolated singularity. So here is what happens in the how to get irreducible case. So this paper was actually follow-up to my paper with Kohler, but was published earlier. So I proved the following, that every finitely presented group appears as fundamental group for some irreducible two-dimensional projective variety, whose singularities are normal crossing. So irreducible is good, that's what Simpson was after. Singularities are normal crossings, and they're Z2 quotients. They're called Whitney umbrellas, they're given by this equation. I did not know what they are. I just wrote to Kohler, here is what I proved. Okay, let me draw a picture of these Z2 quotients, because that's how I think of Whitney umbrellas. So you take C2, you take another C2, inside of C3, and this is C1, where they meet, and this is the origin. You take involution, which swaps the two C2s, and it induces map -1 on the intersection. Involution tau, and then you take the quotient by tau. So Whitney umbrella is singularity at the origin of the quotient. So I wrote to Kohler, I said, okay, so what is it called? He said, congratulations, Misha, you discovered Whitney umbrella. So I knew that there is such a thing as Whitney umbrella, but I only used regular umbrellas before. So that's Whitney umbrella, and right, so notice that there is this one more type of singularity that appears in this theorem, and here I'm saying that irreducible variety with normal crossings and nothing else. So I was stuck on this Whitney umbrellas for 3 years until I finally proved that. So that's the kind of the optimal result. Namely, every finitely represented group appears as fundamental group of some irreducible two-dimensional. Dimension 2 is the first dimension where it can happen. Because in dimension 1, these are just, fundamental groups are just free products of surface groups and free groups. Very boring. But in dimension 2, you can get any group you want. So variety whose no irreducible projective variety, singularities are just normal crossings. So that's what happened last year. So the proof of this theorem, I will not talk at all about this isolated singularities. I will talk about how to get this varieties with normal crossings, irreducible varieties. It's a combination of some three-dimensional hyperbolic geometry and topology and some few other things, but mostly. And the mystery here is, what does it have to do with the problem? I mean, what do these three-dimensional hyperbolic orbifolds, which I'm using, have to do with the algebraic varieties? So what we'll do something that hyperbolic geometers like and know, which is something very classical. It's called Dirichlet fundamental domains. So we'll convert them to complex projective varieties with normal crossing singularities and prescribed fundamental groups. That's what we are going to do. So here is the diagram. So we start with the group presentation. And group presentation, we just have a bunch of letters and words in these letters, right? That's a group presentation, just completely combinatorial object. Okay, we will convert this first to hyperbolic three-dimensional orbifold, and that's already a mystery. I mean, how do you convert this equation? I mean, these words into three-dimensional orbifolds, and then from this we will go to the Dirichlet domains of the fundamental groups of these orbifolds. Okay, some tilings of hyperbolic three space. And then, so again, in my earlier work, I went from here directly to the projective variety. So the trick is to go from something which is three-dimensional, go to something five-dimensional. So it turns out that in order to reduce dimension to 2, you first have to increase it to 5. That was the kind of magic. That's how I got rid of Whitney umbrellas. So we'll go, I mean, going from three-dimensional discrete groups to five-dimensional discrete groups, it's kind of easy. It's a construction which is due to Poincaré. Just kind of the almost obvious extension of isometries from hyperbolic 3 space to hyperbolic 5 space. So, we'll use the Dirichlet domains and then convert this to projective varieties. So the mystery here really is, I mean, there are several mysteries. To go from here to here, then what are these generic Dirichlet domains? This is not a mystery. This is another mystery. And I will explain what I can during the talk, and whatever I don't explain, I don't. Okay? So let's get started. I mean, again, there are several interesting parts to the story. So I will start with the proof of not really Simpson's theorem, but Deline's theorem, namely this one, where you don't care about irreducible, don't care about singularities, but you want to realize the given fundamental group. Okay? Group as a fundamental group. So here is what it is. It's, I mean, if you learn anything from my talk, please learn this, because it's such a beautiful thing. So we'll start with a finite simplicial complex, and everybody knows what it means here, right? So, and everybody knows that every finitely represented group appears as a fundamental group of such a complex. Again, that's something which we learn from algebraic topology class, right? If you have a finite presentation of a group, you build a CW complex just by attaching the cells. And then, of course, you can convert CW complex into simplicial complex. Everything stays finite. So that's kind of, that's a graduate material from algebraic topology class. Okay, so what do we do now? And then you take this simplicial complex and realize it as a subcomplex of some n-dimensional simplex. And again, that's something obvious. So there are some faces you will be missing. Well, you add them until you get a full simplex. It's like every simple graph is a subgraph of a complete graph, right? But if you do not have an edge between two vertices, you insert this edge, and so on. Okay, that's again something very, very trivial. So some simplex delta n. Now this simplex sits in the affine space, right? Okay, so what we'll do, we'll complexify this. We'll complexify this simplicial complex, namely extend every phase to its complex projective span. Right, again, a real affine space is a part of real projective space, right? But just by adding hyperplane to infinity, and then you can complexify everything, right? So it sits in a complex projective space. Now, every simplex I replace with the smallest complex projective space containing the simplex. For example, point replaced by point, of course. H is replaced by complex projective line, and so on, right? So, I mean, it's absolutely canonical construction, right? So, what's the result? Now, I will take the union of these projective subspaces, okay? Well, it's a union of projective subspaces in a complex projective space. And it's easy to see it's a variety. I mean, you can just write down equations. Every linear subspace is just solution set of system of linear equations. Then just multiply them, okay? So it's manifestly projective variety. Okay, what happens to fundamental group? Fundamental group doesn't change because combinatorics of this new thing is exactly the same as it was before. You just apply Van Kampen's theorem if you want. And I should say that projective spaces are simply connected. You don't introduce anything else to fundamental group. Instead of introducing a relator, right, by adding a phase, you introduce relator by adding something simply connected, like CP2. But Van Kampen's theorem doesn't care what you attach, as long as it's simply connected. So that's the proof, okay? Combinatorics did not change, it's manifestly projective, fundamental group did not change either. End of the proof, okay? So the next page is illustration of this process. So suppose my C was maybe a complete graph on 4 vertices. Again, here I draw only few. I mean, so now you take an edge, for example, this edge, and complexify, or this edge, and extend it to, I can draw only a real projective line. But you can have to imagine complex projective line. And then take the union. So it's a union of projective lines in projective space. And of course, you see, it's not going to be normal crossings, right? If, say, you have, okay, if you have only 2 edges meeting together, yes. You have 2 complex lines meeting together. But suppose, like in this picture, you have 3 edges meeting at this point. Then you have 3 coordinate lines. That's not a normal crossing, right? You have to have 3 coordinate hyperplanes meeting together to get normal crossing. This is not a normal crossing, okay? It's also highly reducible. I mean, it's kind of manifestly clear, right? Because you literally break this as a union of CP1s, right? None of them is contained in another. So it's manifestly highly reducible. Again, unless you're extremely lucky with, if you're lucky, you just probably get a trivial group. Okay, so again, it will violate all these other properties, but at least it will realize the correct fundamental group. Okay? So you want to imitate this construction or generalize it. All right, so the only, so again, if you think about this complexification, so the only way to get a normal crossing, say here, is to say instead of 3 lines, you want to have 3 planes meeting together, right? So in other words, what we want our simplicial complex locally. Suppose it's 2-dimensional. Dimension 2 is the key dimension, right? Because that's where you realize the given fundamental group. So let's pretend it's 3-dimensional complex. So you want to have 3 faces meeting together at a point, right? Then you think of this as a boundary of coordinate quadrant, or octant, sorry, in 3-dimensional space. You complexify it, it's a normal crossing. So that's what we want, right? We want this kind of local combinatorics. Okay, assuming it's 2-dimensional. Right, so we want to have something which locally looks like a corner of Euclidean, whatever, not octant, but whatever it is in high dimensions. So simplicial complexes are not good enough for this. One needs to generalize the notion of simplicial complex. And that's some generalization which is actually well known, so I will describe this. It's a kind of Euclidean, or I will use hyperbolic, but you can assume for a moment it's Euclidean thing. And that's what we're using with color. We are using Euclidean complexes. It's a Euclidean or hyperbolic polyhedral complex. It's a generalization of a simplicial complex. So what is it? So the faces are possibly unbounded, I'm allowing this, convex polyhedron. Okay, what is convex polyhedron? It's just a set of given by some intersection of half spaces, right? Closed or open, I mean, it depends. That's a convex polyhedron. And it makes sense in a Euclidean space or hyperbolic space. And if you like, you can think of a Klein model of hyperbolic space where really convex polyhedra are Euclidean convex polyhedra. Not more, not less. Okay? So these are faces. Again, to define simplicial complex, what do you need? You need notion of a cell, and you need incidence maps, right? Well, that's what we're going to do here. So instance maps are isometric embeddings of cells into cells as faces. Just ignore this part, it's kind of irrelevant. In a simplicial complex, one face embeds into another face in a unique way. So you can, one can require this as well, but it's not very important. Okay, so that's the, and once you have this, then you have this polyhedral complex. And again, we did not invent this, this was known. This kind of construction is well known. So examples. Every simplicial complex is a Euclidean, say Euclidean polyhedral complex. Why? Simplicial complex, of course, doesn't have any metric, right? But we can declare every simplex to be a regular Euclidean simplex with unit edges. Then, of course, all affine instance maps become Euclidean isometric maps. And we can play the same game hyperbolically if you want, because we can declare every simplex to be a regular hyperbolic simplex with unit edge side edges. Okay. Another example is, but that's boring because it's simplicial. A more interesting example is cubulations, where cells will be cubes. Just take a standard cubulation of Euclidean space. Well, faces are cubes of various dimensions, and instance maps are various inclusions. Another map maybe is something which you also learn in algebraic topology class is this, right? You take a square and you glue sides of the square together, right? I mean, that's a Euclidean polyhedral complex which gives us a torus or Klein-Bottle depending on what we want to achieve, right? That's another Euclidean polyhedral complex. Just a square with identified edges, okay? So another example that we actually are going to use is what's called Voronoi tessellation of Rn. Again, I will really need hyperbolic space, and I will explain what it is on the next page. Okay, it's something which was invented, a long time ago, over 100 years ago. So let's start with the discrete subset of Rn or Hn. Oh boy. So Voronoi complex is defined by its facets, top-dimensional cells. So namely, for every point of this discrete set, we define its Voronoi cell as a set of points in the ambient space, points y, which are closer to x than to all other points of uppercase x. Okay. Again, points which are closer to x than to all other points. So I will draw the picture. So I will draw it in a very, very primitive example. Suppose my set is x consists of only 2 points. Maybe it's x1 and this is x2, and I'm, say, in hyperbolic space, hyperbolic plane, for example. Okay. So what is the Voronoi cell of x1? These are points which are closer to x1 than to x2. What will be the boundary? These are points which are equidistant from x1 and x2, right? So just draw a bisector. Here, x1 distance from y to x1 is equal to the distance from y to x2. And beauty of hyperbolic geometry, it is a hyperplane, right? So this is Voronoi cell v of x1. This is the Voronoi cell v of x2. But you can imagine what it looks like for more general configurations of points. But again, why hyperbolic geometry? Because this boundary is a hyperplane. So this is really a cell, right? So it's a polyhedron. So cells are polyhedron. So an example that we'll be using is the following. It's called Dirichlet-Tallien. So we start with a discrete group of isometries of hyperbolic n space. Pick a point, it will be some generic point x. Look at the orbit of this point. This orbit is a discrete subset of hyperbolic space. And now we take the Tallien. And this is the kind of pictures that you see in, say, Coxeter Talliens of hyperbolic space or whatnot, right? Again, it's hard to draw, but I will try to draw, say, Voronoi Tallien of hyperbolic plane, Tallien by Dirichlet domains. So this is hyperbolic plane, this is my center. Maybe, there are infinitely many points in the orbit, of course, right? But then you look at the points which are closer to this point than to this point, closer to this point than to this point, right? So that's the cell of the point x1, okay? Some kind of polygon. And then you can imagine that this thing continues because you have a similar tile around every point in this orbit. So that's a tiling of hyperbolic space by convex polyhedra. Okay. Whether Dirichlet knew about this, I don't know, because I'm not sure he knew about hyperbolic space. I think it was Poincaré who attributed, who just called them Dirichlet domains rather than Dirichlet himself. So Dirichlet was talking about Euclidean. I mean, there is the same construction in Euclidean space. That's what Dirichlet was using. So, right. So that's supposed to be a picture of, say, 4 points. Yeah. So this is tiling for 4-point set. This is the dual, which is called Delaunay triangulation. So given any points, I mean, I'm again taking this 4-point set, which is very primitive. For example, I connect the two vertical points. Again, vertices of the dual triangulation are points of my original set. Edges, whenever two tiles meet along a hyperface, I connect them by an edge, and so on. Okay, so that's the dual complex. Simplicial complex. The trick is sometimes it's simplicial complex, sometimes it's not. Okay. Here in this picture, the dual is a simplicial complex, and then this Voronoi complex is called simple. So in this example, Voronoi complex is simple. For example, here at this point, 3 faces meet together, right? So the dual one is a simplicial complex. Incidentally, Delaunay was a student of Voronoi. So Voronoi was a Russian mathematician from early 20th century, and Delaunay was his student. Right. Again, one defines similarly simplicity for general polyhedral complexes, but we'll need it only for this Dirichlet tilings. So this is an example of simple, and this is an example of non-simple. Right here, 4 faces meet together at one point. The dual one is, this is a square, it's not a simplex. Okay, so this one is bad, this one is good. Okay, but now you probably realize, why do I care? Because this will give me normal crossings, right? And this will not. Here, if I try to complexify this, it will give me 4 complex planes meeting at one point. That's not a normal crossing. Here, I will have 3 complex planes meeting at one point. That's a normal crossing. So I do want to have these simple tilings, okay, or simple complexes. So now we'll try to play the same game as D-line, okay? We'll pretend to be Pierre D-line, and we'll see what happens, okay? I mean, I kind of knew about this construction when Kohler wrote to me. So, and that's why I was optimistic that this thing will work. So, okay, so for every phase of our complex, again, think of this complex as being completely disassembled. Again, simplicial complexes sit in the simplex, right? This complex, just think about this torus, it doesn't sit anywhere, right? You just have to disassemble it and say, okay, this H sits in its own projective space, and so on, okay? So now what we'll do for every phase, we'll take its complex projective span. We'll just replace it with projective space of the same dimension. Complex dimension, of course. And then incidence maps of faces, they're isometric embeddings, right? And the beauty of this is that there's a Klein model of hyperbolic geometry, right? Where hyperbolic isometries are, they're linear transformations, they're projective. So we can complexify them and make them into complex projective transformations, right? So the incidence maps will be linear, right? Linear embeddings of projective spaces of various dimensions, right? So we obtain this complex, which is collection of various projective spaces of various dimensions, and the linear maps between them, kind of embeddings of smaller to bigger. Okay, that's a complex of projective spaces. Okay. So I'm using Klein model. So okay, so assume that the C is finite. Okay, we're in trouble because here for this Dirichlet tiling, it's typically infinite. If my group is infinite, I will have an infinite tiling. So, and finite groups I don't care about. That's too primitive. So that's why that's an assumption. Assuming C is finite, we would like to take a push out of this complex. Okay, for a topology, I want to glue things together. Okay, using these linear maps, and call it Y. And I rolled this to Kohler and said, of course, this push out will be projective variety. I was very naive. I'm not algebraic geometry. Topologies, of course, as a topologist, you can just glue things together and everything works. So now in simplicial case, what you do, you just take the union, right? Just take a union of linear subspace of various dimensions. Here we actually have to glue. So now it's actually much less obvious that the push out is a variety, and it's not clear why it's projective. And Kohler constructed various counterexamples to what I was saying. So this might not be a variety in general, and if it is a variety, it might not be projective. Okay. And without Kohler, it would take me forever to make it work. So, but I was lucky because he's one of the best algebraic geometers around. So, okay, here's another problem. Before, when we were doing this simplicial complex construction, combinatorics did not change. If two edges of a simplex meet at a point, their linear spans meet exactly the same point, right? And the same for other intersections. Look what happens if you try to play the same game with polyhedra. Let's just take this trapezoid, right? Take these two edges, A and B, they're disjoint, right? Take the linear spans, PA and PB, wow, they intersect. Combinatorics changed. So we'll be in trouble applying Van Kampen's theorem, okay? That's definitely a problem, okay? Okay, now anybody who knows anything about algebraic geometry knows what to do here. You do this, as Alberto would, right? You blow up, okay? I mean, you have to organize blow up correctly, so you first blow up vertices, then you blow up lines, and so on. But this thing is clear. We call them parasitic intersections. We get rid of parasites. We kind of invite these fumigators and just, we fumigate this complex. So get rid of parasites. Okay, fine. So we do blow up. Okay, the result is not a complex of projective spaces. Well, it's a complex of projective rational varieties. And not that much different. They're still simply connected. We can still play the same game, right? Now the other okay, this is a parasitic intersection, right? So probably Kohler had to work, but this work, it's actually, the idea is very simple. It's beautiful and simple because all these examples, they were unnatural counterexamples. This is a natural constructions. Okay, how do you prove that something is a projective variety? You want to, if you know algebraic geometry, you want to construct an ample line bundle and then take sections. Okay, you are staring at projective space. It has God-given ample line bundles, say hyperplane bundle. Linear maps carry hyperplanes to hyperplanes, right? So these line bundles match. They stay ample. Okay, blow up, you modify the line bundle. But that's how you produce, or not you, but Kohler. That's how he produced the ample line bundle and therefore got projective embedding. Okay, so this part was actually quite easy to do in the retrospect. Okay. So outcome is a projective variety whose singularities are normal crossings. Okay, assuming that we are in this situation, right? A priori, look at the picture which I drew. Here I have actually fourfold intersection, right? You might or might not get lucky with this thing, right? Assume that you have this simple complex. So then the result is a variety with normal crossings, so that fundamental group did not change as before. Because again, we are gluing together simply connected things. Okay. Let's see. Okay. Now, if you think about Euclidean or hyperbolic, if this X consists of more than one point, it will never be irreducible, right? Because every tile will be replaced by projective space of the same dimension, right? So you have as many top dimensional projective spaces, so blown up projective spaces, as many tiles you have, okay? So this construction is manifestly reducible, okay? So it's definitely an issue there, right? Again, if I say take something like this, say take this point, and this point, and look at the tiling, it definitely will be reducible, okay? And that's why in this paper with Kohler, we were using Euclidean tiling, so we were getting reducible varieties for this reason. So on the other hand, so again, this issue with simple tiling, let's just set it aside for a moment. Okay, let's just concentrate on how to get irreducible variety. Somehow I want to say that there is only one maximal tile, right? because every tile will give us irreducible component. Okay, so luckily, if you think about this picture, there is a natural way to reduce all these infinitely many tiles just to one tile, right? Because the group gamma acts transitively, right? We took an orbit of the group gamma, and every point of the orbit is a tile. If you take the quotient of this tiling by gamma, there is only one tile left, okay? So that's why discrete groups show up here, okay? So you take a discrete group, so this guy acts transitively on the faces, on the facets, on top dimensional faces. So the quotient complex has single facet. Facet is a maximal face, okay? So that's where irreducible will come from the fact that we have unique maximal tile. So discrete groups help, okay? So assume for a moment this thing is simple. That's where the hard work will be. So this complex, this quotient complex will be simple as well. And again, assuming this quotient complex is finite, like in this case, in this picture, we have just a polygon, right? With finitely many edges, glue edges together, everything is finite, right? But in general, a discrete group can have infinitely many faces of Dirichlet domain. That's a kind of separate issue. So take complexification as above, we get an irreducible projective variety with normal crossing singularities only, okay? So there are several ifs here, right? The main one is why it would be simple, okay? And then, like less of an issue, why this quotient complex is finite. Furthermore, if you think about this fundamental group of this quotient is the same as the fundamental group of a quotient of the hyperbolic space by the discrete group. Because, I mean, you glue together, right? So if you identify faces of this domain, you get a quotient manifold if you have a torsion-free group, but orbifold if you have torsion, and will have torsion. So fundamental group doesn't change, but again, it's important that this result is not the group gamma itself, right? Because if I get torsion-free group gamma, then the quotient has the same fundamental group as the group gamma, and I don't get arbitrary group, because arbitrary groups do not act on hyperbolic space discretely. And I want to get arbitrary groups as my fundamental groups. So I need to have elements of finite order, so this group is not gamma, okay? So here is a conjecture, how to deal with this non-generic issue which I described here, this kind of non-simple tiling, that if gamma is a torsion-free group, which will not happen in our case, we need torsion, but just for simplicity I'm stating this for torsion-free groups, then for generic choice of X, generic it's kind of clear what it means here, just take out some union, countable union of proper subvarieties, okay, that's what generic means. This complex is simple. I mean, it's a very attractive and natural conjecture, because if you think about this, if you just take a bunch of points in Euclidean space and just wiggle these points independently, the result in Voronoi tiling will be simple. You'll be just destroying all these multiple intersections. The problem here, we have only one point to wiggle. The rest is given by the group. We don't have as much freedom. Okay. Okay, so this conjecture used to be a theorem. This is never good. I mean, when Kova wrote to me, I knew this as a theorem. That's why I was optimistic. Used to be a theorem due to Jorgensen and Martin, 1986. The proof turned out to be hopelessly wrong. It was discovered by Diaz and Ushijima. I found this by accident. I want to check who else referred to this paper by Martin and Jorgensen, because I needed some mild generalization, because I had torsion, and realized that they found a mistake. And the mistake was horrible. I mean, in mathematics, usually how it works, you find, say, one good idea and use it repeatedly. They found one bad idea and use it repeatedly. They just wiped out the entire proof. I mean, there is absolutely nothing left. I mean, the mistake was they confused algebraic and semi-algebraic. They thought something was algebraic subvariety, turned out to be only semi-algebraic, and that makes a world of difference. So, I mean, the entire paper became, I mean, the conjecture is still there, but the paper became useless. Okay, so here is a theorem which I proved. That's how to deal with this. Suppose we have a discrete subgroup, has no unipotent elements, and every finite order element is what's called Cartan involution. Cartan involution is just a point reflection. You take a transformation, if you, in the union ball model, suppose you have a center of the ball, take x goes to minus x. That's Cartan involution. Has a unique fixed point. Okay, so, and we need this, we'll need these elements of finite order. Okay, so every element of constant order, then for generic choice of X, the complex is simple away from vertices. And so, which means that along every edge, only 3 tiles meet. Vertices I don't know, I still don't know. Already this was quite hard, but vertices are unimportant. We can remove them without changing fundamental group. We're in dimension 3 after all, okay? So it's harmless to remove vertices. So, okay. And again, that was one of the difficult parts of the proof, proving this. A corollary is that, suppose that gamma is a discrete convex compact, okay, that gives you this no unipotent elements and finitely sided Dirichlet domain. Finitely sided is necessary if you were to construct something decent, because we want to have only finitely many faces in the end. So where every non-trivial element is Cartan, finite order is Cartan, then there exists an irreducible 3-dimensional projective variety Y, whose singularities are normal crossings, and there are Z2 quotients. So that fundamental group of this Y is isomorphic to fundamental group of the quotient orbifold. Okay, where are the Z2 quotients? Let me explain. So remember, I have these Cartan evolutions, right? So here is the Dirichlet domain of a Voronoi tile of a point X. Here is a Voronoi tile of point gamma X, where gamma is Cartan. So where is the fixed point of this Cartan? Well, Cartan has to interchange this tile and this tile, right? Fixed point beta beyond the boundary, right? So this is where fixed point is. How does it act on the boundary? Well, by -1, right? It's -1. Now you recognize 3-dimensional version of this Whitney umbrella, right? Because when you complexify, what do you get? You get C3, you get another C3, meeting along C2, and here you have an involution that swaps them and has a fixed point. It's a 3-dimensional version of Whitney umbrella. Okay. Okay, I will finish in 5 minutes. Sorry, I want to put. So the question is, okay, I promised you arbitrary groups. So far I got these groups which look awfully similar to discrete groups of isometries of hyperbolic 3 space. How complicated this could be. So here is, right, so notice that this quotient is a 3-dimensional manifold, apart from projections of these fixed points. At projections, these are just projective cones over RP2. Right? If you take a 3-dimensional ball, divide by antipodal map, this is cone over RP2, that's all. Okay? So they're almost 3-dimensional manifolds. The question is, how complicated could be the fundamental groups of these objects? So here is a minor variation on a theorem of Panov and Petrunin. By luck, this paper was posted on the archive 1 week before Kovar wrote to me. Except I didn't believe this paper. So here is what it says. So every finitely represented group there exists some discrete subgroup of isometries of hyperbolic. Just if you don't know, just ignore this. It just gives you finiteness of number of faces. So that every non-trivial element is Cartan, and G is a fundamental group of the quotient space. To me, as a 3-dimensional topologist, I'm part-time 3-dimensional topologist, this is absolutely astounding. Because the fundamental groups of 3-dimensional manifolds are very, very restricted. These objects which appear here are almost 3-dimensional manifolds. You just have these mildest singularities, cone over RP2, right? And you can realize any finitely represented group this way. So for about a week, I was trying to prove that this theorem cannot be true, because I mean, it was written in such a way that I just couldn't believe that. I mean, I was a referee, I mean, they know all this. I was a referee of this paper. So I made them actually write down a decent proof. So I could believe that. So, but yes, so apparently it then turned out that it was first discovered by Casson, Andrew Casson, in 1980s. And if you know about Casson, Casson never writes himself. Unless somebody writes for him, the stuff just disappears. And nobody wrote it for him, so this guy just, had to do the hard work instead of Casson. But it's something that I believe every 3-dimensional topologist needs to know, that there are these things which are very close to 3-dimensional manifolds, which have arbitrary fundamental groups. And now, once we put this, again, they allow some elliptic rotations, but for this theorem, for these rotations, theorem about generic differential domains fails. So it's really one needs Cartel involutions. So combining these theorems, we get that for every finite represented group, there exists a three-dimensional projective variety whose singularities are normal crossings and their Z2 quotients. Okay. And I promised for you get irreducible you get, but I promised only normal crossings, and yeah, fortunately for this there is very little time. So the trick is, yeah. I mean, so how do you get two-dimensional? Let's ignore this Whitney umbrella business. How do you get two-dimensional variety out of this? Use Lefschetz hyperplanes. I mean, use Goretzky-McPherson version of Lefschetz hyperplane sections theorem. You intersect this variety with some generic hyperplane. It stays projective by Bertini's theorem, and the fundamental group doesn't change. Okay. Again, Lefschetz did it for smooth manifolds, for smooth varieties, but they improved it to some. I mean, it's not true for general ones, but these are nice varieties. So fundamental group doesn't change. So singularities will be Whitney umbrellas, normal crossings and Whitney umbrellas coming from not really these fixed points, because one point you can miss, right? If you have one point in a variety, generic hyperplane will miss it. But these Cartel evolutions have bigger fixed point set. Namely, antipodal map fixes entire hyperplane at infinity. That's the guy which produces Whitney umbrella. And yeah. So how to get rid of this? One has to increase dimension into 5. Take this discrete group, embed it into isometry group of high-dimensional space, and play the same game. And then you can get rid of Whitney umbrellas. But I stop here. Thank you. I want to put something here just for your entertainment. History was, so there is a person who was playing prominent role here, he was Boris Nikolaevich Delaunay. So how did he get his French name? And this is clearly French, right? So surname of his French ancestors, Delaunay. Captured in Russia during the Russian War of 1812. You know, there is American War of 1812, which Mexicans probably might know about, but Russians know about Russian War of 1812. So, and he was captured. Incidentally, he was a nephew of the last Bastille governor, Marquis Delaunay, who was, of course, killed during the French Revolution, during the event. Right, so, and he had two very good students. One of them was A.D. Alexandrov, most famous for this kind of geometric geometry, and the other was Shafarevich, most famous for number theory and algebraic geometry, and that's a theme of this talk. Okay, so now, right.
Silo, is it possible to explain the transition from Mumford to Perelman or no?
Okay, so let me tell you the story. Okay, question is, are there questions more related to this? Okay.
Yes.
Okay, maybe.
I mean, in the cohomology of algebraic varieties, you have this finer structure, which is this mixed Hodge structure. In the case of smooth, you already use.
Right, you use, right.
And then you're only using H1.
Right,
so
here.
H1, in any singular algebraic variety, you have this weight filtration.
Right.
And the quotient of the weight filtration gives you pure Hodge structure polarization.
Right.
Can this mixed Hodge structure in H1 induce some structure?
I see, so you're saying that, right, so they should, I mean, there is definitely, I mean, this is known, again, this goes back to a work of, I mean, in the smooth case, it goes back to Deligne, where there is Deligne, Griffith, Sullivan, and then in the quasi-projective space, it's Morgan, it's 1970s. So again, there is a way to produce, kind of extract information about, in the smooth case, I know how it works. In the single case, I never thought about this. In the smooth case, indeed, there is the mixed Hodge structure, which in the singular case, in the quasi-projective case, comes from singularities which you attach when you compactify. There is a mixed Hodge, there is information about fundamental group which one extracts from the mixed Hodge structure. In the singular case, I don't know. I assume the answer is yes, but again, from this viewpoint, you're absolutely right, there might be restrictions on somehow, if you enhance the fundamental group, if you kind of impose more information, namely coming from this mixed Hodge structure, there might be more restrictions on groups. Equipped with this extra whatever we call it, filtration. Don't know what. I don't know the answer though. But there is a very good chance there are restrictions, non-trivial restrictions. Yes. Yes.
If you desingularize your number of crossings, what do you get? Nothing. You're going to change change
yeah. Well, okay. So the question is how to desingularize. One can argue that's as non-singular as it could be. Of course, in say dimension one, you can do this, but then it completely change fundamental. Just change. Right. So I mean, basically, that's like the atom. You can, or this like elementary particle. That's kind of as simple, as basic as it can get. You cannot really do much else with this thing, right? So it's you cannot desingularize it any further in any meaningful way once it's normal crossing. That's in particular that's why algebraic geometries like them. These are kind of the simplest things which you cannot simplify any further. So that question is how many people want to hear about Perelman? No. Yeah. Okay. So here is the story, and one person, I think Walter knows about this because he's coming exactly from this stuff, right? So, but he might be the only person in this room who knows about the story. So, I discovered this by accident, complete accident. So, in 1960, David Mumford wrote a paper. I think publications of HES, if I remember correctly. He was interested in the following: two-dimensional isolated singularity, and the link is simply connected. And of course, at the time, Poincare conjecture was wide open. He was interested in, is it a sphere in this case? And he proved it is. More importantly, how he proved it. He realized that there is this kind of decomposition of this link as a union of solid tori. And then from this, that's still not enough. It's still unclear why, if something is simply connected in a union of solid tori, it's a sphere. But he managed to do it by some sort of cut and paste method. Nothing was known at the time. Again, three-dimensional topology was in infancy, essentially. So, but he did it. And then, Hirzebruch had a student, but named Walthausen. Walthausen got an assignment. Read this paper by Mumford and see what's there. So Walthausen discovered the structure, union of solid tori, is really can be put as a kind of general structure of three-dimensional manifold. So he wrote a paper in German in English it's called On a Class of Three-Dimensional Manifolds. It's the most obscure title imaginable. But this class was obtained in two different ways. You can describe it as union of solid tori, or you just glue them on the boundaries, not just somehow, but you glue them on boundary pieces. Or you can describe them by basically take maybe surfaces cross circles, surfaces of high genus maybe, and you glue them together along boundary tori. And then he proved that, this manifold breaks into pieces. Some of these pieces will be highly non-simply connected. They're called Seifert pieces. And some of these pieces may be simply connected. So this manifold breaks as a connected sum of this, what we now call graph manifolds. That became part of three-dimensional topology. That's where much of this the geometric decomposition of three-dimensional manifolds grew up from. But then Grisha Perelman, when he was proving geometrization conjecture, he was actually proving that when you take this Ricci flow run into infinity, the manifold breaks into pieces, which are unions of the Seifert pieces, hyperbolic pieces, and solid tori. So the boundary tori might be compressible. And so in the case of Seifert manifolds, it could be it. So it could be just a union, and there is no way to prevent this from happening, namely this union of Seifert manifolds plus solid tori. And he just said it satisfies geometrization conjecture. And it's not obvious, but that's what Walthausen proved in his 1967 paper, which goes back to David Mumford. The idea was going back to David Mumford. So Perelman actually needed this piece of, again, he did not need any three-dimensional topology in his proof, but he needed this. He did not know about it, though. People observed this later on. But, yeah, so that's Mumford's contribution to geometrization of three-dimensional manifolds. I like this story because it illustrates this kind of connectedness of mathematics.
Would be settled on this.
Yeah.